All right. Do you guys see me and the slideshow?
Yeah.
Beautiful. Now you just see the slideshow?
Yep.
Okay, awesome. Um, so I scaled this back quite a bit because normally this would take us a lot of time to kind of go through kind of every little single part. I'm going to just, uh, I'm not even going to get through this entire slideshow, actually. I'm just going to go through a concept called buffered solutions. And what I did was I kind of put in some cheat codes here that might help you with what we did yesterday with the common ion effect. So it's kind of like when you in calculus and you learn derivatives the long way, then you learn the short way. Today is the short way. Does not require an ice table. So it's kind of nice. There's a couple little things that we can do with it. So what we're going to do first is we're going to talk about what a buffer is. You guys have had enough biology and classes where you've probably investigated buffers or maybe even heard this term. For us, what a buffer is a solution that can contain or that does contain conjugate acid-base pairs. And what happens is that this creates a situation where these solutions can resist drastic changes to pH if you added a strong acid or a strong base. So let me translate that for you. Your blood has to stay within a very, very narrow range of pH. And this is because when your blood gets too acidic, you learned this in college biology, I'm sure you'll do a lab on this. It's called denaturing proteins. When the blood gets too acidic or too alkaline, it messes with the proteins and like the hemoglobin molecule, because a lot of those things are held by hydrogen bonds, or their shape is very dependent on hydrogen bonds. So long story short, your blood's got to stay in a certain pH. And so you have a couple of chemicals in your blood that one is an acid, one is a base. And what they do is they kind of counteract any addition of strong acid or strong base or weak acid, weak base. Okay. You're probably like, well, how the heck does my blood get acidic? Well, it has to do with carbon dioxide and oxygen levels. All right. We won't get into that too much. Seawater is also a buffer. Who cares about that? So here's why buffers resist drastic changes. Buffers can resist drastic changes in pH because they contain an acidic species. Yeah, they use the word species. I don't have to tell you. Species that can react with the OH. Okay. So there's something in the buffer that if we dumped in some OH, there's an acid portion that kind of neutralizes the OH. A buffer also has a basic species that if you decided to dump some strong acid in there, it can neutralize that and react with the H+. So that's what buffers do. We're going to talk about how buffers can be calculated in this class. If you're in a biochemistry or biology class, like many of you guys would probably take, you're going to get an all-you-can-eat buffet of buffers in that class, just because. But chemistry is where we talk about just how much they change the pH. You won't do these calculations probably in maybe a biochem class. I don't know. So, what's in a buffer? A buffer is a weak acid or a base plus a salt that contains a conjugate of the acid or base. So sometimes it's just easier to see examples of these. And what a buffer does is it uses the common ion effect. So like what we looked at yesterday, those examples we did yesterday would actually produce buffers. So here's an example. A buffer could be made if you took HF, which is a weak acid, and then you mixed in some NaF, because the F minus is a conjugate weak base. You could also make a buffer that involves a weak base, NH3, and then a weak conjugate acid like the NH4 plus. Okay. So those are going to be the things that are in buffers. And by the way, when we go through these slideshows, I'm going to probably come out of it and I'm going to have some stuff I don't want you to write down. Okay. So like this one, I don't even think I want you to write anything down here, because I'll probably go to the board and try to explain this a little bit better. All right. So I am going to go to the board. I'm going to show you guys what I'm talking about here. And you don't have to write any of this stuff down. Can you guys see me? I know Jaylee can see me.
Yeah.
Okay, perfect. So here's what I'm talking about. So let's just say we have hx, which who cares what x is? This is f minus whatever, right? It's just a weak acid. Okay. Now, yesterday we looked at the common ion effect. That what we said is if we have this solution and we dump a salt that has some X minus in it, it's going to kind of push the equilibrium back. Okay. So when we were calculating the pH, I'm going to go ahead and write the Ka for this. The Ka for this would be, oh, that's a bad bracket. Like I said, I'm just trying to get through kind of the guts of this. Okay, so in equilibrium, we would find the Ka of this is equal to that, and that at equilibrium. Well, what we're concerned with today is that. So I'm going to rearrange this a little bit. Like I said, you don't have to write this down. Just want you to see what's happening here. Once again, a terrible bracket. I think I did my algebra right. Multiplied that, divided that. Okay, so H plus is dependent on, and today, this is going to be our little shortcut equation that we will use, not this one, something that's a little bit better. It does a little bit of logarithmic stuff. So H plus is dependent on two things, what I want you to see. It's going to be dependent on the Ka, and then it's going to be dependent kind of sort of on this ratio of conjugates to each other. That's going to be our goal, and that's going to be what we look at with our delightful equation today. Okay, so I want you to write that down. That's just some algebra, just kind of showing you guys where the stuff's coming from. So when we actually use the equation, you guys will kind of remember that. You remember the K is important, and the ratio of these things is important. Okay, so that's going to be what we look at today. So I'm going to just skip down here. Okay, I'm going to just stay here. And I'm going to show you how buffers work. This is also in the slideshow, but I can't draw in the slideshow. So let me just show you real quick. All right, let's say we have, this is going to be really stupid. Obviously, this would not. This is a mixture. Today, we're going to make a buffer of HF and F minus. Now, how'd that F minus get in there? LIF, NAF, doesn't matter. The group 1 metal, we don't care. So I hope you guys understand that this is a solution. These guys are just kind of swimming around. They're intermixed evenly. I'm just going to pretend that all the HF goes on this side, all the F minus goes on this side, which is totally stupid. That's not a thing. So what would happen if, and this is how buffers work. If this situation is our buffer here, okay? So if I said, hey, I'm going to dump some HCl into this. I'm going to just dump some HCl, and I'm going to just crush that with some strong acid. Well, dumping HCl would be putting H plus in there. Now, here's what a buffer does. A buffer takes one of these two parts and it reacts with the thing that you're throwing it in there. So, like, if I were to dump some H plus in here, this is an acid. It's going to be neutralized by the base. So the F minus would gobble this little booger up right here. Okay. So as we dump this H plus in, the F minus, and I'll just go ahead and write the equation for you, which is going to be pretty obvious. You guys will go, oh yeah, that is what it makes. So notice that it makes more of this stuff. So if I dump the H plus in here, what happens is the F minus value goes down and the HF value goes up. Now, you might go, okay, well, no kidding, man. Of course, that's what's going to happen. What this buffer does, though, is it kind of takes this strong acid that we're adding, and it neutralizes it, and the pH won't be such a drastic change because the HF, or this weak acid, is the thing that's moving up. Okay, so that's what buffers do. They just they fight against those things. Now, let's say I took this same buffer here and I dumped in, instead of some, let's do NaOH. I dumped in a base. So I threw some base in here. Well, dumping a base in here is going to be like dumping OH minus. OH minus is going to be neutralized by the acid. And then that, in this case, it'll be the HF. So HF plus OH, you'll notice that this reaction makes HOH, which makes more water. This is all swimming around in water anyway. And it makes more F minus. So this would just produce the exact opposite. The HF value would go down because it's gobbled up by this OH minus, and the F minus value would go up. That's how buffers work. So the pH you would expect to get by dumping a strong base in is not as drastic because it's kind of being replaced with this weak base. That's how buffers work. Okay? So our goal today is going to be calculating this, and you guys can calculate this using ICE tables and the common ion effect. But for us, I'm going to show you a shortcut. Okay? All right. So this is the greatest equation in the history of acid-base chemistry. I think it's a pretty good one. I don't know if it's the greatest per se, but it's pretty good. It's going to have some stuff that you haven't seen yet because like I said, we're on a time crunch. We're on a amount of time that I'm talking to you guys crunch, and I'm not going to go into every little detail here. So you're going to see something that's a little bit different, but trust me, you guys have had enough chemistry. You can understand this and figure this out. Okay. This equation is called the Henderson-Hasselbalch equation. I call it the H and H equation because it's just too much writing, and I always spell Hasselbalch wrong. So the H and H equation is going to be what we use to calculate the pH of a buffer anytime the common ion effect is involved. So here's the Henderson-Hasselbalch equation. It is pH equals, very important, you get this little P in front of this, pKa. You know, what the heck's pKa? pH equals pKa plus the log of the ratio of the base to the acid. pH equals pKa plus the log of the ratio of base to acid. Okay. So question is, what have you not seen that's up there? Anybody know?
pKa.
pKa. All right. So here's the deal, guys. In chemistry, if you see a P in front of anything, it means negative log. So the pKa is the negative log of a Ka. Make sure you get that down somewhere, okay? If you see a lowercase p in front of anything, that lowercase p means negative log. So when we say pH, it's the negative log of the H plus. We say POH, it's a negative log of the OH minus. So PKB would be the negative log of a KB. Same idea. Keep that in mind. Write that down. Negative log of Ka. So that's the thing you haven't seen yet, but that's not a big deal. That's just a button in your calculator. Okay? Do you have your calculator, Beanie? Okay, I don't have mine here, so I guess we'll just have to deal with it when it comes. All right. So we use this to find the pH of a buffer. And so this means that we don't have to use an ICE table in order to find the pH of something that has a common ion effect. Okay. And actually, it's more accurate because you don't have to worry about that whole quadratic thing when it's ionized too much. So here's what we're going to do. We're going to find the pH of 0.12 molar lactic acid with 0.10 molar sodium lactate. It does not matter if you don't know what lactic acid is. You guys can just look this up on Appendix D. So you guys are going to need Appendix D here real quick. All right. So 0.12 molar lactic acid. I'm just going to call it HA because I don't want to write everything out. And 0.1 molar sodium lactate. Okay. Actually, I'll write it H-lac just so we can. Okay. Do you have Appendix D, Beanie?
Yeah.
Okay. So.
You want it?
Yeah, I do want it. I'm very ill prepared, guys. All right, so what we do is we look on our little chart here for the thing that is on the Appendix D. Either it's going to be a base or it's going to be an acid, okay? In this case, I see that lactic acid has a Ka of 1.4 times 10 to the negative fourth. Okay? So I'm going to exit out of this and I'll show you guys how to plug this into the Henderson-Hasselbalch. All right. So Henderson-Hasselbalch basically says if we want a pH of this solution, we're going to take the negative log of the Ka plus the log of the base to the acid ratio. And this is the thing you have to be able to identify. So lactic acid is going to be the 0.12 on the bottom. Sodium lactate, once again, this is a group 1 metal. Shank it. We don't care about it. That's going to be its conjugate. So we would just do that, right? So we would do that. I'm going to pause the recording real quick and run and grab my calculator. Okay, so my answer, I got 3.77 for my pH of my buffer. I don't know what you guys got. Give you guys a second to figure that out. Unmute and ask questions if you have them. Anybody get that? Maybe.
Yeah.
You guys got that?
I got that.
Okay, cool. So are we good there? Can I move on? Something I want you guys to get in your notes, very important here. Okay. Is this. Not when buffers get dominated. Good Lord. Is this. Both things. So these acids and bases, and this is why this equation is kind of sweet, is the acid and base can be given to you in molarity, like it was in this problem, or it can be in moles as well. So we can use molarity or moles. The thinking behind that is sometimes it's more convenient to use molarities, and sometimes it's more convenient to use moles. And if we're dumping these things together, hopefully it makes sense to you guys that dumping these things together, these things would have the same volume. The acid and the base would be in the same solution with the same volume. So essentially the volumes can cancel out. So it's sometimes nice to just have moles given to us. So you don't have to deal with molarity and all that business, which, like I said, is pretty sweet. Okay? So that's a Henderson-Hasselbalch equation. Now, here's a variation. Let's say you don't want pH. You want POH. I don't know why you'd want POH, but maybe you do. The H and H equation can be reversed to apply to bases. So POH, now pay attention here, is equal to PKB, plus the log of the acid over the base. So it's kind of the opposite. Every part is the opposite. The opposite of pH is POH. The opposite of pKa is PKB. And the log is flipped. So in the previous one, it was base over acid. This one, it's acid over base. We would use that when it's more convenient. When, like, for example, I guess we'll probably do one. We can do one real quick. Maybe we want the POH. I don't know. Maybe we have a base that's given to us. Okay, I'll make one up real quick. So 0.15 NH3, 0.12. All right, here's one made up real quick for you. Okay, so on the board, we have 0.15 molar NH3 and 0.12 molar NH4Cl. So the idea and the thinking behind this is, well, I got to find either a Ka or a Kb. For us, it's more convenient to find the Kb of this guy because that thing's written on Appendix D. All right? So because this is a base with a Kb, we're thinking it's going to be a more alkaline or base-like solution. So maybe you want the pH. Well, that's great. We can do the pH at the end. There's lots of different ways to do this. Let's just use this new variation. POH is equal to PKB. So the Kb of NH3 is 1.8 times 10 to the negative fifth plus the log of the acid. You'd have to know which one's the acid. It's the conjugate here over the base. All right? So negative log 1.8 e negative 5 plus the log 0.12 divided by 0.15. All right. POH is equal to 4.65. So that means that our pH, if we cared about that, is somewhere around 9.35. Like I said, you can round this, however, it doesn't matter.
So I have a question.
Fire away.
Could you just get the pOH by subtracting
Mhm.
14? Like instead of doing this way?
Yeah, so like Jay would just ask, could you just get the pOH by subtracting? So like, but here's the problem, Jay. You got to have a Ka.
Oh yeah.
So
Okay.
what you'd have to do is divide by K dub
Okay.
to find the K of that one. And then, like I said, there's lots of different ways you can do this, but it's just a little equation to help you out. Hopefully it does. All right. Okay, let's do one with moles, and then it will stop, and we'll stop the recording and take your questions or whatever. Okay, so how many moles of NH4Cl must be added to 2.5 liters of 0.1 molar NH3 to form a buffer whose pH is 9? Whoa. Now, you were doing this with an ice table. I got 2 words for you. Brain bleed. Okay, maybe not. But it would be kind of gross. So I'm going to let you guys get that down. I'm going to write this stuff on the board so I can go to the board in a second. So we have NH4Cl. Hopefully by now you guys are understanding that the Cl doesn't mean crap. We've got, so we want to know moles of this. We got 2.5 liters of a 0.1 molar NH3. Okay. Man, this is busy. Okay, I'm kind of glad we just did that KB example though, because for this example, and our goal, we want the pH to be equal to 9, right? So this is college stuff right here. This is pretty advanced stuff. But like I said, once you get comfortable and you get some reps using the Henderson-Hasselbalch, and I'm just telling you, it ain't going to be this year. It's going to be next year probably. All right. This year is going to be, our reps are going to be pretty limited, but this is advanced stuff here. Okay. So let me go through the thought process on how we would solve this, because this has kind of got a little bit of everything. All right. So the reason the Henderson-Hasselbalch equation is nice because you can use molarity or moles. Okay. The question is, how many moles of NH4Cl would we have to add? Well, I'm just going to go ahead and get rid of the Cl minus because I don't care about that. Okay. All right. So our Henderson-Hasselbalch that we're going to use, we want the pH to be 9. But here's what I want to show you guys. It would probably be more convenient for us to use the pOH equation simply because we're using NH3 here. And NH3 has a Kb like I showed you a second ago. Okay? And that's an easy fix, right? Because pH of 9 would be a pOH of what? 5? Okay? If you're wondering how I got that, I just subtracted 14 from 9. I got 5. Okay? So let's use the Henderson-Hasselbalch. Let's just kind of plug some stuff in here. Okay? So I'm going to use the pOH one because, once again, I can just look up Kb easily for this one. If it was one that was involving an acid, I would just use the pH one. Okay, so the pOH is equal to 5. That's equal to the negative log of 1.8 times 10 to the negative 5th. That's the Kb for NH3, plus the log of the acid over the base. Okay, well, the acid is going to be what we're looking for. Moles of NH3. That's the acid. We need, if we're doing moles here, then we've got to put moles down here. So a little refresher course here. If that's molarity and that's volume, all right, molarity is equal to moles over liters. So we take 0.1 times 2.5, we get 0.25 moles of NH3. Now all we're doing is we're solving for X. Okay, we're solving for X. All right, I'm going to push pause and let you guys solve for X here. Or see if you guys can solve. Let's resume here. All right, so here's the deal. The negative log of this value is 4.74. That's going to be 5 is equal to 4.74 plus the log of X over 0.25. Okay, I'm going to subtract this over first. If I'm insulting your intelligence, I apologize. So I get about 0.255 or 256 here. Okay, that's equal to the log of X over 0.25. Now, to deal with a logarithm, we have to, it's a log base 10, so we kind of have to do that business to cancel out the logarithm. We have to take 10 to the 0.26, and we get 1.8. 10 to the log shanks that. So we have X is over 0.25, and then we take 1.8 times 0.25, and we get X is equal to 0.45 moles of NH3 or NH4Cl. Okay? Do you guys follow the algebra there?
Yeah.
That makes sense. I don't know how long it's been since you guys have dealt with logarithms like that, algebraically. Probably a while, maybe. I don't know.
I think last year, but
Last year? Okay, I'm going to stop the recording, then we'll just hang on it if you have any questions.